So the next project from Georgia.
Yes. Hello.
Good morning.
Hello from Tbilisi, Georgia. I'm Mario Bujawa.
Anand Water. Our team member Sandro is not here because of COVID.
We represent Georgian American High School. We are pleased to be part of this International Student Science Project competition. In this project, we will be talking about one relationship in a cyclic regular pentagon. For proving our new theorem, we will be using Van Schutten's theorem, Ptolemy's theorem, and golden ratio that we got information about from Wikipedia.
Van Schutten was a Dutch mathematician in the 17th century who developed a wonderful theorem and proved that if a equilateral triangle is inscribed in a circle, then for any arbitrary point on the circle, distances from this point to the most distant vertex of the triangle equals to the sum of the distances from this point to the other two. We discussed generalization of this theorem for regular pentagon with 5 distances. We were lucky to get the results others have not seen yet.
Another theorem we used was Ptolemy's theorem. Ptolemy was a Greek mathematician in the 3rd century. Van Schutten's theorem too was the consequence of Ptolemy's following theorem. In a cyclic quadrilateral, the product of the lengths of its diagonals is equal to the product of the lengths of the pairs of opposite sides. We also used very famous and unique mathematical relationship, golden ratio. Golden ratio is the ratio when the division of the total by the larger equals to the ratio of the larger by the shorter. Phi equals to 1 plus square root of 5 over 2. We use golden ratios features in regular pentagon.
So, in general, regular pentagon is kind of pentagon where all the sides are the same. Therefore, all the diagonals of the pentagon are equal to. Pentagon in total has 5 diagonals. For our graph, ABCDE is a cyclic regular pentagon and P an arbitrary point on the circle. Let's denote distances from the point P to the vertices A, B, C, D, and E, respectively by D1, D2, D3, D4, and D5. Let sides of the pentagon be A and diagonals of the pentagon D. Now, what are we using golden ratio for? It turns out that in regular pentagon, ratio of a diagonal to a side is golden ratio, from which diagonal is equal to product of golden ratio and the side.
We wanted to find relations from any arbitrary point on the circle to a vertex of the regular pentagon. After days of hard work, we got the results we were hoping for. We drew the quadrilaterals in the pentagon, and for every quadrilateral, one by one, used Ptolemy's theorem. Hard part was to clarify what quadrilaterals to use. And now consider quadrilateral APDE. Using Ptolemy's theorem for quadrilaterals yields D1 times A plus D4 times A equals to D5 times D. Firstly, we replaced the by phi multiplied by A, and then simplified the equation dividing both sides of it by A, and we got first equation.
Now consider quadrilateral BPCD. Using Ptolemy's theorem, we get that D2 multiplied by A plus D3 multiplied by D equals to D4 multiplied by A. Firstly, we are going to replace D with phi times A. Afterwards, we are going to simplify the equation and divide both sides of it by A, which will give us second equation. Now we are going to consider quadrilateral ABPC. Here too, we're going to use the same way to simplify the equation. Replace D with A and divide both sides of equation by A, which will lead us to third equation. These are all the 3 equations we got in previous slides. Here we are going to start by summarizing second and third equation. Afterwards, we are going to write down what phi d5 equals to, and afterwards we're going to replace previous equation with the result of the previous equation. We're going to insert a fifth. We know that by definition of phi, we have that phi plus 1 equals to phi squared. We are going to insert fifth and fourth, simplify the equation, which will give us sixth equation and theorem 1. For a regular pentagon ABCDE with the point P on its circumcircle, the length of its diagonals of the 5 line segments connecting P with the vertices of pentagon equals to the product of golden ratio and sum of 2 shorter lengths.
From first formula, we got seventh equation that leads us to second theorem. For a regular pentagon ABCDE with a point P on its circumcircle, the length of longest of the 5 line segments connecting P with the vertices of the pentagon equals to the product of the reciprocal golden ratio and the sum of 2 longer lengths. By multiplying 6th and 7th formulas, we get 8th equation that gives us third theorem. For a regular pentagon ABCDE with a point P on its circumcircle, the square of length of longest of the 5 line segments connecting P with the vertices of the pentagon equals to the product of the sum of 2 shorter lengths and sum of 2 longer lengths. P squared equals to PB plus PC times PA plus PD.
We looked for similar relations that we could not find, but we came across other relations in Wikipedia that is easy to prove using our 5th and 6th equations. First of all, we are going to replace d2 plus d3 with 6th equation, then simplify it, which will give us a formula for the same result as one given in Wikipedia. d2 plus d3 plus d5 equals to d1 plus d4. These are all the references we used for our project. Thank you for your time and attention.
Thank you so much. Okay, so you are senior high school, right?
We're 10th graders, we're freshmen. Juniors.
You are? Sorry?
We are 10th graders, juniors in high school.
Junior high school, that's good. Okay. Can you propose, can I see the fourth slide, please?
Yes.
Okay. So starting from that point, so what was the main objective for you?
We wanted to generalize one-sided theorem, and we generalized it for regular pentagon with 5 distances.
Okay. And is there any application for your project in our real life?
Yes.
It should be useful for something, right? For something engineering or
It might be used in mathematical equations and it will be used for pure math,
yes.
like Van Schutter's theorem and Ptolemy's theorem.
Okay.
Yes, because we proved Van Schutter's theorem, we generalized it to regular pentagon. So it will be used in pure math, just like Van Schutter's theorem and Ptolemy's theorem and other theorems we got here.
Even pure mathematics have a way to use it in applied mathematics. So thank you so much for the clarity of the presentation. It was good, and it was well done. So thank you so much, and good luck for the rest of the contest.
Thank you. Goodbye.
Thank you. Bye bye.